Hello, welcome to this video on inductors. I will attempt in this video to give you some background on inductors that will be helpful in your labs. We start first maybe by discussing what's an inductor. An inductor is a component that's usually made of a number of turns of a coil. We call it a coil. So we have a wire and you create from that out a number of turns. When a current flows in this coil, it creates actually a magnetic field in its volume. So you can get a strong magnetic field. It's not electric field like a capacitor. Magnetic field flowing inside the volume of that coil, and this magnetic field will store energy, but this energy is stored now in the form of magnetic energy. According to Faraday's law, these are the two governing equations relating to current and the voltage. And by the way, for these equations to hold, if this is the polarity of the inductor voltage, the inductor current is assumed to be flowing from positive to negative through the inductor. So the voltage is proportional to the derivative of the current, and the current is proportional to the integral of the voltage. This is opposite to the capacitor. This is the opposite case of the capacitor. Okay, so here the current will have to change smoothly. The current cannot undergo sudden changes, because I can show you here. If I have a current like this, say you have a change in current like this. This is 3 milliamps, and this one here is 1 milliamps. A change like this is not allowed for inductors. Why? Because simply the derivative at this point of the inductor current will be infinity. It went down by 2 milliamps in zero time. But if this derivative is infinite, this means you will have infinite voltage, which is not physical. So the current through the inductor will have to always change in a smooth way. So it will have to go down gradually and slowly from 3 to 1. Okay. On the other hand, the inductor voltage can change abruptly. There is no problem. It can change direction suddenly from 3 to -3 or whatever the case it is. This can happen for an inductor. Okay, so this is the opposite of the capacitor. In the capacitor, the voltage will have to change smoothly, but the current can reverse direction instantaneously. Here, the current will have to change smoothly, but the voltage can change its polarity instantaneously. One last thing to know that this is a linear inductor, so the flux going through this inductor is given by Li. It's linearly proportional to the current, and the constant of proportionality is what we call the inductance in the inductance value. So it's called an inductor, and its main characteristic is the inductance. In the same way we talk about a capacitor, and the main characteristic is the capacitance. The current here is considered positive, okay, as we agreed. And when you have current like this means that simply more energy is being stored. More energy is accumulating in the volume of these coils. If you have something like this, if the polarity is changed like that, this means that it's not it's actually in the discharging way. The current here will be considered negative. Okay, now we consider this circuit here. This circuit it represents an inductor in one loop. You have a battery 5 volts. You have a resistor. This switch was opened before time 0. Okay, and there was no current in the circuit because the circuit was opened. This is the direction of the inductor current, and this is the inductor voltage. So just before we close the switch, so at time 0 minus means just before you close the switch, there was no current in the circuit. The inductor current is equal to 0. The current in the circuit is equal to 0. Now you close the switch, so now the circuit is one loop. Okay, the inductor current cannot change instantaneously. It has to change in a smooth way. Because it was 0 just before you close the switch, it's gonna remain 0 just after you close the switch. So this is how I write this. I say the inductor current immediately after you close the switch will still be 0. It cannot change instantaneously. Now, before you close the switch, VL was 0. VL was 0 because there was no voltage, no current, no flux, nothing. You close the switch. After you close the switch, there is still no current in the circuit because of this condition. Because IL immediately after the closed circuit will still be 0. This means there is no drop across the resistor because there is no current. So where this whole 5 volt will go, it will appear across VL. So VL suddenly, after you close the switch, change from 0 to 5. It will go through a step. And the voltage, as I said, across the resistor will be 0 because current is equal to 0 immediately after I close the switch. Of course, it's going to change later as time passes. Okay? So this is very important to remember. I'm going to repeat this again because this is so important. When the switch was open, there was no current in the circuit. VL is 0, IL is 0, everything is 0. Okay? Once you close the switch, the current in the inductor cannot change instantaneously. It has to change in a smooth way. Because it was 0, 0 just before you close the switch, it will still stay 0 just after you close the switch. So the current will still be 0. If the current is 0, this means that VR is 0. The voltage across the resistor is 0. But 5 volts is equal to VR plus VL. Then VL will have to be equal to 5 volts immediately after you close the switch. Okay, so this is very interesting. VL changes instantaneously from 0 to 5. Now, what's going to happen as time passes? In the beginning, the current is 0. The current will start to build up. Okay, current will start to increase. And when the current is increasing this way, we say that the inductor is charging. So the concept of an inductor charging means that the current is building up. It's opposite to the concept of charging for a capacitor. For a capacitor, we talk about voltage increasing or voltage decreasing, whatever. Actually, for that, we could say it's increasing. Here we talk about current increasing. Okay, so the as time passes, what's gonna happen? The inductor current will build up, will increase, and one other phenomenon I'm going to show you will happen because the inductor current is increasing. VR will increase. VR is the voltage across this resistor here. So this is VR. Okay, this is VR because the current is increasing in this circuit. VR will increase, but 5 volts is equal to VR plus VL. Then VL will start to go down. Okay, at infinity, what's going to happen? We reach steady state. Steady state means the inductor is fully charged. What do we mean by the inductor is fully charged? It reached its maximum possible current. And when that happens, the inductor voltage will be equal to 0. VL will be equal to 0. Its current will be the maximum value it can get. The whole 5 volts will appear across VR. And this is something all electrical engineers know about an inductor. An inductor at steady state in DC, and when you have now DC, when all the transients have died out, is going to represent short circuit, meaning VL is 0. Of course, IL will not be 0. IL actually you can calculate its value. IL, if this is 5 volts, the whole 5 volts will appear across R. Then the current in the circuit is 5 over R. Then IL at infinity is 5 over R. Okay, so this is how things are going to change. Gradually and slowly with time, the inductor current will increase, VR will increase, VL will go down. At steady state, after a sufficiently long time, VL will be 0. The whole 5 volts will appear across the resistor, and the current in the circuit is 5 over R, which is the maximum value the inductor current will get. And the inductor will represent short circuit because VL in this case is equal to 0. Very important to understand that VL, when VL is 0, does not mean that IL is 0. Very important. In the previous slide, we gave a qualitative description of what's going to happen. Let's now have an analytic solution of this. You close the switch at time 0, you have this loop, current will start to flow. What is the governing equation? It's KVL. 5 is equal to VR plus VL. This is the equation that you have. Replace VL by L dIL by dt, because for an inductor the voltage is proportional to the derivative of the current and the constant of proportionality is L. Replace VR is the voltage here, but this VR is equal to IR, and this I is the same I as IL, so I can replace VR by IL. Now divide both sides by L and reorganize the equation to obtain this first order ordinary differential equation. This is the differential equation you have seen before in your calculus courses, and its solution will have a homogeneous solution and a particular integral solution. You obtain the homogeneous solution by making this term equal to 0. You obtain the particular integral solution by considering this term here, which is 5 over L. So what we did, we divide both sides by L, okay, and we reorganize the equation. If you put this term equal to 0, you get dIL by dt plus r over L. IL is equal to 0. IL is a function of time, and you can look at it like, if you consider IL like y and t is x, so this is what's telling you dy by dx plus a constant multiplying y is equal to 0. It's a typical ordinary differential equation, and its solution is a decaying exponential. This is something you have studied in your calculus courses. Now, if you consider the analytic part, you will see that the particular integral part, will give you a constant. So this term will disappear. So you have r over L IL is equal to 5 over L, or IL is equal to 5 over r. Okay, so for the particular integral, we say when you have a constant excitation, then the particular integral part is a constant, and if it is a constant, then this term is 0. Then that constant solution is 5 over L divided by r over L, so it's going to give you 5 over r. Okay, so this slide just summarizes the things I mentioned earlier. To get the homogeneous solution, this is IL homogeneous. You set the excitation to 0, but this one has an analytic solution, which is a decaying exponential, and its solution is I naught e to the minus r over LT. Remember, R is the resistance given, L is the inductance is given, I naught is a constant we have to determine. Okay, it depends on the initial conditions. We can reorganize this in the form that most electrical engineers are familiar with, e to the minus t over tau, and tau is L over r. Tau actually has units of dimensions, or it has units of second. It's second. When you divide inductance in Henry by resistance in ohms, you get seconds. So tau here is called the time constant of the circuit. It determines how fast the inductor current builds. Okay, so the smaller the tau, the faster the charging, the building up of the inductor current is gonna go. Now, as I mentioned in the previous slide, to get the particular integral, when you have a constant here, which is 5 over L, the solution is a constant, and the particular integral is 5 over R. Now, the total inductor current is the sum of the particular integral solution plus the homogeneous solution. Now, we have now to impose the initial conditions to find the constant I naught. Tau we know. Tau is L over R. Okay, we know L, we know R. So we agreed just after you close the switch, the inductor current was 0. Okay, because just before you close the switch it was 0. Just after you close the switch it's gonna stay 0. So if you put here t equal to 0, you get I naught plus 5 over R is equal to 0. This term is 0 at time 0. Put t equal to 0, you get 0 equal to 5 over R plus I naught, or I naught is equal to minus 5 over R. So this is the expression of the inductor current as a function of time. For the charging case, it's 5 over R, 1 minus e to the minus t over tau. So at time t equal to 0, this exponential term will give you 1. 1 minus 1 will give you 0. So indeed, we start with 0. As time goes to infinity, this exponential term will give you 0, and you reach a steady state of 5 over R. So this is the maximum current that the inductor can charge to. So remember, when I talk about an inductor charging, I mean that its current is building up. Okay, this is very important to remember. This is opposite to the capacitor. When we talk about the capacitor charging, we mean that its voltage is building up. Okay, let's get a feeling of the numbers. So if you have here in the previous circuit I've shown you, if the resistance has a value of 1 kilo ohm, the inductance is 1 millihenry, 10 to the minus 3, then tau is L over R, 10 to the minus 3 divided by 1k will give you 1 microsecond, 10 to the minus 6 seconds. And the steady state current, or the current, the peak current of the inductor is 5 over R. So 5 over 1k, so it's going to be 5 milliamps. So this is how the inductor current changes with time. Starts with 0 and gradually and slowly, using this expression that we derived, is going to build up to 5 milliamps at infinity. Okay, tau determines how fast this current grows. So I rewrote the current for you again here. This is T over tau. But tau is 10 to the minus 6. So I can write this at e to the minus 10 to the power 6 t. So I replaced 1 over tau by 10 to the power 6. Okay, so if t is equal to tau, which is 10 to the minus 6, then 10 to the minus 6 multiplying 10 to the power 6 will give you 1. E to the minus 1 is 1 over 2.87. So it's about 1/3, a little bit more than 1/3. So here this means that at time tau, the current have risen to 5 multiplying 1 minus maybe minus 0.35 or something. Okay, maybe it goes up to 0.66 something of its maximum value. So it will go up to 3 milliamps or something. Okay, so the smaller the tau, the faster the charging. So if tau is smaller than this, then what you're going to be getting is something like this. Say, faster charging of the inductor current. What if tau is smaller? It's going to be even smaller charging of the inductor current. Okay, so tau and the resistance will determine how fast this charging of the current is happening. Okay, now we switch to the discharging case. So I'm gonna consider this situation. We had a voltage of 5 volts from minus infinity to 0. So the circuit already reached its steady state. So the current, so in this circuit here, the circuit has been like this for a very long time. This is 5 volts, okay? And as a result, the inductor voltage is now 0, as we agreed. When all the transients die out, the inductor voltage will be 0. The current, this 5 volts, will appear completely across VR, and the current is 5 over R. Okay, so this is the inductor current. Now, at time 0, this voltage suddenly dropped from 5 to 0. Okay, so the excitation disappeared. So this became short circuit. This became like a short circuit, because when you have a shorted voltage source, this means when you have a voltage source of value 0, this means that you have effectively a short circuit. Okay, so I can redraw this circuit again like this. Maybe I can see if I can erase this here. So I can remove this source. Okay, the source is not there. Okay, and I can add this short circuit, and this is how really the circuit looks like. And this is after time 0. So after time 0, the voltage went to 0, and this means that this is short circuit. Remember, we had current I flowing this way, so keep in mind, the current I was flowing this way, and its value is 5 over R. Okay, when that happened. Now, the inductor current cannot change its value instantaneously. It's like a wheel that's turning. You cannot suddenly stop it, okay? So what's going to happen? The inductor current will still to flow in this direction, okay? But we have a little bit of a strange situation, because at time before this happened, before the voltage disappeared, the whole 5 volts was appearing across the R, the resistor R, okay? Now the battery disappeared. The current still the same. So this means that at time 0 plus, VR was equal to 5. So this means that VL at time 0 plus will be equal to minus 5. So you see what is happening? The inductor current suddenly changed from 0 here, just before this change happened, to minus 5 here. Okay, I'm gonna repeat this again. Why do we have that? Remember, we had here a battery, okay? We had this battery for a long time. Its value was 5 volts. But the inductor was at steady state, so VL was 0. So this 5 was equal to VR. So VR was 5. Now, the battery disappeared. It became short circuit. Okay, the current cannot change instantaneously, so the current will still be 5 over R even after the battery disappeared, because as we agreed, the inductor current cannot change instantaneously. It has to change in a smooth way. It will still be 5 over R. So this means that the VR immediately after you remove the battery will still be 5 volts. So this means, take a look at KVL, apply KVL here. If this is 5 volts, then this is minus 5 volts. So this is a very interesting development. So the inductor voltage can change its polarity instantaneously, while the inductor current cannot change its value instantaneously, change in a smooth way. So this is what I'm saying. Just before just before this change in the battery voltage happened, there was a current in the circuit, and it reached its maximum value of 5 over R. Okay? Now, after that change happened here, the current will still be 5 over R immediately after. I mean, when I say 0 plus, I mean immediately after that change. It's gonna, of course, decay with time. Now, before you make that change, there was no voltage across the inductor, because the inductor was at steady state. Okay, the current is fully charged, and we are done with that. So VL is 0. Now, if after you made that change here to satisfy KVL, VL immediately after that change will change to minus 5 volts. Okay, so this is what's happening. So the current will continue to go to flow in this circuit, but this means that it's supplying power to the resistor. Where does this power go? Where does this power come from? It comes from the energy stored in the inductor magnetic field, the magnetic field of the inductor. So the current still flows in this direction. Okay, it's supplying power to the resistor, and as a result, the current will start to die out gradually and slowly with time, and the magnetic field inside the inductor will die with time, gradually and slowly. Okay, and then until at infinity everything is zero. VL is zero, IL is zero, VR is zero, and the energy has completely dissipated in the resistor. Now, this is an analytical description of what's happening. Sorry, a qualitative description. Let's go now to analytical description. This is the circuit that we have. This is what we defined as VR. Okay, so I redraw this circuit again here. This is VR and this is VL. Then the governing equation from KVL is that VL is minus VR. This is the governing equation. But what is VL? It is proportional to the derivative of the current, inductor current. What is VR? The way this is the inductor current here. This is the inductor current, okay? Then you can see VR is ILR. If I move this one to the other side, I have this homogeneous differential equation, first order differential equation. And we have seen in the other case, in the case we discussed already, that this one has an exponential solution. So it's going to be I naught e to the minus t over tau. And this is what I predicted, because the current still flowing here, even though the current is still flowing, but the circuit does not have an excitation anymore. Then the energy stored in the inductor's magnetic field will be dissipated gradually and slowly and supplied in the form of power to the resistor. And the resistor will dissipate that, and as a result, gradually and slowly the current will start to die. Everything is going to die out with time until at infinity the coil is completely dissipated. Okay, so it lost all its energy, and there is no voltage or current anywhere in the circuit. Now, this equation, as I said, has an exponential solution, e to the I naught e to the minus t over tau, and tau is L over R, as we explained in the previous slides. Okay, so I wrote here the current expression, I naught e to the minus R L R over LT, and we write it again in the form that we are more familiar with, e to the minus t over tau, where tau is L over R. And L over R has units of seconds, and it's called the time constant. Now, we started when the battery voltage disappeared, the initial value of the inductor current was 5 over R. So if we put here t equal to 0, this term will give you 1. Then I naught is IL at time 0, which is 5 over R. Then this is how the inductor current expression looks like. Okay, it's 5 over r e to the minus t over tau. So it starts at time 0 with 5 over r and then gradually and slowly decay with time because the inductor is discharging. By the way, notice that discharging means that it's losing its current, is dying out gradually and slowly. Okay, of what is happening to the voltage here? I'm not showing it in this diagram. What's happening to the voltage? The voltage, I'm going to draw it on the same diagram, but of course it's a different scale. It starts at time 0 with minus 5. And then it will also, if you take into account that the voltage is the derivative of the current. So if you go back and you differentiate this expression, VL is L dIL by dt. So you differentiate this one and multiply it by L, you will see that the current actually starts with 5 and then gradually and slowly as well decays to 0. So at infinity, the current is 0, the voltage is 0, the inductor does not have any energy, it's completely discharged. Okay, so this is the case of a discharging inductor, and again it behaves opposite to the case of a charging inductor. The thing that I want you to remember is that the inductor current does not change instantaneously, it has to change in a smooth way, while the inductor voltage can change polarity instantaneously. Okay, let's have an example here. So this is an example of a discharging inductor. If the resistance is 1 kilo ohm and the inductance is 1 Henry, then tau is L over R. So L is 1 divided by 10 to the power 3, get 1 milliseconds. Okay, so this means that the inductor voltage will drop to almost 1/3 of its original value, and the inductor current will drop to 1/3 of its original value after 1 milliseconds. It's approximately 1/3. Okay, so this is I. This is the expression for I. It's 5 over r. This is the initial value I note, e to the minus t over tau. But I replaced 1 over tau, where tau is 1 milliseconds by 1000. Okay, so this is the expression here, and remember R is 1k, so 5 over 1k will give you 5 milliamps. So I wrote it as 5 e to the minus 1000 t milliamps. This is the expression for the inductor current. Okay, I can add the subscript L here. It's not really necessary. We know that we're talking about the inductor current. How does the inductor voltage looks like? Inductor voltage is a derivative of the inductor current multiplying by L. So L is 1. Okay, if you differentiate e to the minus 1000 t, you get minus 1000 e to the minus 1000 t. And remember, you have milli here, so I multiply by 10 to the minus 3. So 10 to the minus 3 will cancel with 10 to the power 3. You get a minus sign. So this is how the inductor voltage looks like. Again, as we agreed, starts with minus 5 and then gradually and slowly decays to 0. Okay, so it's decaying towards 0, and then where the inductor would have lost all its energy, and the energy, as I said, is stored in its magnetic field. Okay, what will happen if you have a square wave? So it's a train of pulses. Train of pulses is shown here. So it goes up to 5 for a certain time and then drop to 0 and then up to 5 and then 0 and then up to 5 and so on. So if you have that applied to this circuit, what's going to happen in the very beginning? If the inductor does not have any current, the current will rise from 0 and then gradually and slowly it will rise to a certain, it's not 5 here, I'm not drawing it, it's not the same scale. The current has its own scale, okay, but I'm showing it as fully charged. So remember, this value here is not 5, this value is actually 5 over r if it's fully charged. So will the inductor be fully charged or not? Well, it depends on how the time constant, which is L over r, compares to the width of this square wave. If this width is sufficiently big, we have sufficient time within this positive pulse to charge the inductor, then the inductor current will reach its peak value, which is 5 over r. So remember, this value here is simply 5 over r. Okay, what's gonna happen next? Well, if the input of the excitation drops to 0, the current still flowing this way, okay, but it will still, this is shorted now because it's 0. It will start to supply energy to the inductor, and the current in the inductor will start to weaken gradually and slowly. So you have the inductor discharging. So the current is discharging gradually and slowly from 5 over r. If this if this duration of time is sufficiently large, okay, then it will have approached pretty much zero. Okay, of course, if it's narrow, then it's gonna maybe discharge to maybe may say a fraction of 5 over r. Again, if the pulse repeats, it's gonna go up. It's charged again. If this becomes 5 again, the inductor current will start to charge again. Notice the inductor current is continuous. Right? It's continuous. It does not have any sudden jumps. It does not change from 5 over r to half 5 over r in no time. No, it has to be smooth. What is happening to the inductor voltage here? In the beginning, there was no current here. You had no current in the inductor. Okay? And you had no current in the inductor. Then VR is 0. Then the whole 5 volts will appear across the inductor. So you start with 5. Okay? You start with, let me draw it maybe with a different color. You start with 5. And then it starts gradually and slowly to decay with time. At infinity, the inductor current will go to 0. We agreed that when the current in the inductor it reaches its peak value, its steady state value, the inductor voltage will be 0. This is one of the properties of the inductors. What is happening here in this part? We have a sudden transition from 5 to 0. And as I explained in the previous slides, this is gonna result, the current will still be flowing in the same direction. The inductor current will still be flowing in the same direction, but this is shorted. So VL suddenly, if this is 5, VL suddenly will have to become minus 5. So it will look something like this. So it will start like this here, and then it will start to decay with time, and then it goes to 0. And then it rises again suddenly to 5, and then it decays with time to 0, and then it becomes minus 5, and then it decays to time with time to 0. Okay, so this is the voltage. This is VL. Okay, and this one here is IL, and I'm drawing them on the same graph, but of course they have different scales. Very important to remember that. Okay, so as you could see, the inductor voltage can change abruptly from 0 to minus 5, from 0 to 5, from 0 to minus 5, while the inductor current is continuous. It's changing in a continuous way.